Oh, hello everyone. We're going to start. Today is going to be special because we are going to have a lecture by Professor Mutlu without Professor Mutlu. We are going to play, the lecture is going to be about SIMD processors and GPUs. And, well, this is the agenda for today and for tomorrow, actually. So the videos we are going to play are here. You already have access to these slides. I uploaded them to the website in the morning. And essentially, we will start playing the videos. If you have questions, we can stop the video and we can answer or try to answer the questions. So in theory, we should have time to watch today quite a bit of the videos, but probably we will have to finish with the third one tomorrow. And in the remaining time that we will have tomorrow, I will give you some short introduction about GPU programming that could also be interesting for you and maybe for future labs that we might have. So we are going to start now, unless you have any questions.
Okay, so let's move on to another cool concept, which is SIMD processing. And this is, again, a very widely successful concept. It was not as widely successful before the GPUs. It was relatively specialized. But this hopefully gives you another historical perspective. Times change, constraints change, applications change, and different execution paradigms may be really useful. And I think we may be seeing that with systolic arrays, as I mentioned earlier, right? Google TPU, tensor processing unit, uses systolic arrays, for example. But we'll talk about that when we get to it, if we get to it. So far we've talked about irregular parallelism. VLIW is also for irregular parallelism. The compiler is extracting parallelism out of this mess of code. Actually, the compiler works with the data flow and control flow graphs also and tries to figure out what's independent and dependent. But if the parallelism is regular, you can do something much simpler. So what is a regular parallelism? So let's put a taxonomy into the computation paradigms. This was actually done in 1966 by Mike Flynn, who's retired at Stanford now. But basically, he categorized computer instructions in terms of how many instructions you execute and how many data elements you execute on. So you can have single instruction or multiple instructions, and you can have single data element and multiple data elements. So a single instruction operates on a single data element. This is exactly the ISAs that we were looking at, right? Add instruction operates on a single data element. Whenever I say a single data element, it's really a single scalar data element. So it's really two data elements, but that's it, basically. You add two values. It's not like an add specifies two additions on two pieces of data, two different pieces of data, or for the elements. Basically, you specify only one operation for an add. Single instruction, multiple data. Single instruction operates on multiple data elements. You don't say only do an add of these two numbers, but add these two sequences of numbers, these two arrays, basically. So you can say you're doing this operation on 1,024 different sets of elements. So we'll see array processors and vector processors, and a modern GPU is a combination of both, actually. MISD is a weird concept. Multiple instructions operate on a single data element. So you do add, multiply, or something on a single data element, or a single set of data elements. It's a little bit harder to imagine, but closest form is really systolic array or a streaming processor that we will hopefully get to. But you don't need to bang your head into the wall about it right now. Yes? Okay. I see. Okay, so then you have multiple data elements, you say? Okay, I see. That's a good point, actually. Yeah, I have not thought about that. You can have very specialized forms of these operations that require multiple instructions on single data. Yes, but you can always break that down into multiple instructions also. Yes. Yeah, you could also think about that also. Yeah, exactly. But we'll see the systolic array. So there's arguments as to whether this exists or not. And actually, Flynn's taxonomy didn't talk about that as much. So MIMD is multiple instructions operate on multiple data elements. This is multiple instruction streams, basically. So multi-threading, multiprocessors are really examples of the multiple instruction on multiple data elements paradigm. So they can execute completely independent instructions. So VLIW is an example of SISD, actually, because you really have a single logical instruction, right? You can specify multiple operations, but it's really a single logical operation. And it's lockstep, right? So the instruction doesn't move, even if you complete one of the logical operations. It's really an entity together. So we're going to cover this one. I mean, the advanced architecture course will cover a lot of multiprocessing, and we'll figure out what to do with that. So this is also data parallelism. Basically, in this case, the concurrency doesn't arise from something else that we're going to talk about, but it really arises from performing the same operations on multiple pieces of data, different pieces of data. For example, a dot product of two vectors, or addition of two vectors, matrix multiplication. You're really doing the same operation. Let's do the dot product, basically. It's really doing multiplication on multiple different elements, right? And then addition at the end. But if you're adding two arrays, that's again SIMD, right? If you're copying one string to another, that's SIMD, because you're doing the copy operation many, many times. So contrast this with data flow. In data flow, concurrency arises from executing different operations in parallel. It's really different operations. You don't care about whether they're the same or not, whether they're using the same data element or not, or different data elements or not. It's really data-driven execution. Contrast this with thread or control parallelism. Here, concurrency arises from executing different threads of control in parallel. And whereas SIMD exploits instruction-level parallelism. You have multiple instructions, or more appropriately, operations that are concurrent. Instructions just happen to be the same in this case. Okay, let's take a look at that. So this could happen in time or space. There's this time-space duality, and you need multiple processing elements. So let's look at the time-space duality. So array processor, an instruction, a SIMD instruction, operates on multiple data elements at the same time using different processing units, using different functional units, using different space, basically. We'll see an example of this soon. On a vector processor, an instruction operates on multiple data elements in consecutive time steps using the same processing element. So now you see that a vector processor is more frugal in terms of its hardware usage. You have a functional unit, and you have a SIMD instruction that's, let's say you're doing an add, and you're doing that add on multiple elements of the array, two arrays. Every cycle, you look at a different data element. You add a different data element. In an array processor, every cycle, you do different additions. You do the same addition on different data elements on different processors. So let's look at an example over here. So this is an array processor. You have multiple different processing elements that can all do the same thing. Whereas you have a vector processor that have specialized units, load, add, multiply, store. And we're going to look at this code. And this code looks interesting now because the input over here is an array, right? It's a 4-element array. You're going to load this into a vector register, which consists of 4 elements. Actually, let's take a look at this. So we're going to assume registers are not scalar anymore, but they're really vectors. They store multiple. So basically, you have a vector register, 0, which can store, let's say, 64 elements. 0 through 63. So if you're doing an addition of array A to B, what you can do is you can load 64 elements into vector register 0, and then you can load 64 elements of B into vector register 1. Okay, like this, I guess. And you have a functional unit, add, and then you basically, in consecutive cycles, send 1 element per cycle to the functional unit. That way you do 64 additions in 64 cycles, right? That's it, basically. So it's pretty simple. With one with one instruction, you specify 64 operations. So it's very efficient. That's why the GPUs are very efficient, because they don't have this control overhead. If you think about a single instruction, single data machine, all of these are different adds. It's a different loop. Basically, you do this in a loop, right? Whereas here, we have a single instruction that basically specifies a 64-element loop in a single instruction, single data machine. So if we go back to this example, basically your vector register is 4 entries, and you load the first 4 elements of the array into the vector register, and then this add happens to add one element, increment each element by 1, and this multiplies each element by 2. So you basically are incrementing each element by 1 and then multiplying that by 2. So what you're really computing for each element is 2 times x plus 1, right? 2x plus 2 in the end, and then you're storing the result into back into the memory. Yes.
I don't understand why the vector processor should be any faster than a single instruction machine. I mean, the processor still has to check, still has to do a loop, it still has to go over 64 elements one by one.
Okay, it'll be clear when we go through the performance example. We'll go through a performance example soon, but let's clarify the concepts here. So an array processor, here if you look at this, you have one load instruction operating on 4 different data elements. You can do all of those 4 different data elements operations at the same time. You load element 0, you load element 1, you load element 2, you load element 3 concurrently into the vector register. In the next cycle, you add 1 to element 0, add 1 to element 1, 1 to element 2, 1 to element 3. In the next cycle, you multiply element 0 with 2 and do the same thing on different elements. And the next cycle, you store the resulting results into the different the corresponding locations in memory. So that's the array processor. It's beautiful, right? You're operating with just one instruction. You're doing 4 operations here. Vector processor is the same thing, except you're doing it in time. You load the first element. You're finishing one instruction across time. You load the first element over here, and then in the next cycle, you load the next element. Basically, you're pipelining the load. In the next cycle, you're adding the first element, incrementing the first element. In the next cycle, you're loading the next element, adding the first element, and multiplying the 0th element. In the next cycle, you're loading the third element, adding the second element, multiplying the first element, and storing the 0th one. So this is the steady state where all of your functional units are now busy. And then, of course, you finish the pipeline. So a vector processor is a little bit longer, as you've observed, but this is going to be still faster than a normal machine, and we'll see why. But an array processor does same operation at the same time, whereas a vector processor at the steady state does different operations at the same time. And if you look at the space, meaning different functional units, an array processor does different operations in the same space. That's why it's more expensive. Whereas a vector processor does the same operation at the same space. So a vector processor is a little bit cheaper because your functional units can be different. They don't all have to do the same thing, right? They don't all have to do all of the operations, as you can see over here. Okay, so let's contrast this with VLIW. So remember VLIW, with one single program counter, you fetch multiple operations. These could be independent operations, and they're packed together by the compiler, and logically they're a single instruction after that point. In an array processor, a single operation is encoded this way. You have a program counter. For example, this is an add. But you operate on multiple different data elements. So how do you know how many data elements you operate on? There's another register. That's the vector length. That tells you, oh, I should operate on 4 elements. So whenever I do a load, for example, I calculate a base address. And this vector register says, oh, load the 4 elements starting from that address. So you really do 4 loads to different locations starting from that base address. And we'll see this in more detail soon. So basically, this little instruction that doesn't consume much space gets expanded to many operations internally in the processing element. So VLIW is like this. You still have the encoding overhead. But of course, there's an advantage and disadvantage. The advantage here is irregular parallelism, right? You can exploit irregular parallelism here, whereas you have to rely on regular parallelism, data level parallelism here. Okay, so let's look into some example here. So a vector, hopefully you know what a vector is. It's a two-dimensional, one-dimensional array of numbers, right? And many scientific commercial programs use vectors. Hopefully you programmed with vectors. How many of you did? Okay, good. So you know the concept from math. But this is an example computation. I cooked it up. Basically, for 50 elements, you average two different vectors, right? Element by element. So it's really element-wise average of two different vectors. And store the result into C. So a vector processor is one whose instructions operate on vectors rather than scalar, single data values, right? So if you encode this in a single instruction, single data, I say you have a lot of instructions. So first of all, you need to fetch all of those instructions every other cycle, right? So basic requirements, let's look at the requirements first. You need to load and store vectors. So you need vector registers that contain vectors that I showed you earlier. You need to operate on vectors of different lengths, because you may not always have an array that's 64 entries, right? Actually, sometimes you have 512 entries, which means that you need to stage them into the 64 entry registers. Sometimes you have 4 entries. So you need to have a vector length register that specifies how many elements should this instruction operate on. And your vector length can change. So that's an instruction. You have an instruction that changes the vector length. And elements of a vector might be stored apart from each other in memory. So you need a vector stride register. This will become more clear, but basically stride is the distance between two elements of a vector. Actually, I'll give you an example right now. So you need to, whenever you're doing a load, you need to know how far away these elements are from each other. Consecutive, right? So let me give you an example of matrix multiplication. You guys have done matrix multiplication, I assume, right? So in a matrix multiplication, if I can do this correctly, so let's say this is M things. So you'd better have M over here, right? What you do is you basically take a dot product of this and this, right? So let's assume that this is M is equal to 64. And you lay out the matrix in row major order. So this is row 0, row 1, row 2, dot, dot, dot. Which means that consecutive elements in the row are in consecutive locations in memory. And let's say the base address is A over here. And then let's look at the view of memory over here. Memory is a linear array, and A is here. And we're going to have row 0, element 0 starting at A. Row 0, element 1 starting at A plus 1. Row 0, element 2, A plus 2, dot, 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 all the way to 63. And row 1 starts at A plus 64. So that's the row major order. Consecutive elements in a row are in consecutive locations in memory. So you have basically row 0 here, row 1 here for A, and then 0th element, 1th element, dot, dot, dot. So when you're loading this vector, this row into your vector register, your stride is 1, right? The distance between these elements is 1 in memory, right? Memory address A, memory address A plus 1, A plus 2, A plus 3, dot, dot, dot. So the load instruction can compute its address nicely. But if you look over here, if you store this also in row major order, and now let's say we have n equals, well, I guess in this case it doesn't matter. Okay, let's do something over here. Let's say we have, I'll say this is columns. Columns equals, I don't know. Shall we say 10? 10 sounds good to me. So you have 10 columns over here. Now if you store this in row major order, let's say this starts from address B, the first element of this row over here is at 0, 1, 2, dot, dot, dot. So you have the 10th element, 10th element over here at address 9. So if you look at memory over here, this matrix starts at location B, and its first row is here of 10 elements, and 0, 9. Next element is at 10, and then 19 over here. Next row starts at address 11, B plus 11. Assume all bytes here. Oh no, 20 sounds better, right? 29, and then 30. Now you want to multiply this with this. So when you load this, you you need to load 64 elements with a stride of 1 starting at address A. So it's a vector load, address A. And you need to set your, before that, you need to set your vector length to 64, and you need to set your vector stride to 1. But if you look here, you want to load all of this into a register. Let's assume that you want to load 64 of these. And actually, M is conveniently 64. That's nice. When you need to do this load from B, vector load from B, you need to change, vector length is the same, that's good. You don't need to change that, but you need to change the stride to 10, right? Why? The consecutive elements that you're loading are 10 locations apart in memory, because you've laid out your matrix this way, right? Does that make sense? So you really need to change the vector stride. That means that your load translates to the first element that you want to load is from address B, and then address B plus 10, B plus 20, B plus 30, and you do it until B plus 10 times 63. So basically, oh, you cannot see it. Yeah. Now you can see it. Basically, your vector load really translates to a for loop where you go from I equals 0, I less than vector length, I plus equals stride, or vector stride, load into vector register I guess B, I, right? So if you want to write in high-level language, that's exactly what you're doing here. It's basically a for loop load, and you need a stride because consecutive elements may not be in consecutive locations in memory, and clearly in this case they're not. So this will have impact on performance because you're accessing not sequential locations in memory, but some other locations in memory. So keep this in mind, but that's the concept of stride. Now you have a stride over here. It's really the distance between vector. Okay, I guess we'll have to leave the example for later, but let me give you why this is useful. A vector instruction performs an operation on each element in consecutive cycles, and you can pipeline the vector functional units. So vector functional units can take lots of different operations, and each pipeline stage operates on a different data elements. And vector instructions allow deeper pipelines because there's no dependency between these data elements, right? They're completely independent of each other. You're just doing the same operation on different data elements. There's no control flow, and you have a known stride. Okay, I think I'll stop here because we'll need to go into a detailed example of how this operates and how this outperforms a pipelined processor that's scalar. But now you can, I'll leave the slides for. Vector processor advantages. This is where we were, basically. There are no dependencies within a vector. As a result, you can pipeline, you can parallelize really well. You can have very deep pipelines without any dependencies, and we will see that. Each instruction generates a lot of work. Basically, with a single encoding, you say add, 1,000,000 things happen. In that sense, it's very efficient. In fact, that's one of the reasons why GPUs are very efficient, because with a single instruction, you can specify many, many pieces of work. This is not true in the von Neumann earlier single instruction, single data architecture that we saw, right? An instruction generates only one piece of operation. Add two numbers together instead of adding 1,000,000 pairs of numbers together. This reduces the instruction fetch bandwidth requirements. So in a GPU, for example, instruction fetch is not a problem. It's really the data fetch that's a problem. Highly regular memory access pattern, we just talked about this, and no need to explicitly code loops. There are fewer branches in the instruction sequence. Now, this is not necessarily true, as we will see, because your machine usually can have a small vector register length, but your arrays might be much, much larger, right? So you'll need to explicitly code loops still, but you'll eliminate a lot of branches. So, of course, with every other idea, as you know now, there's always a downside. And the downside of vector processors is it works only if parallelism is regular. If you have this sort of parallelism, this machine is really good at doing it. So vector operations get a big plus plus over here. The problem is it's very inefficient if parallelism is irregular. So that's why you cannot use your GPUs to do, for example, very complicated single-threaded transactions, because you'd be wasting 500 watts of power on this transaction that you could execute much better on an out-of-order Intel processor. For example, searching for a key in a linked list. If that's what you're doing, if that's the only thing you're doing and there's not much parallelism, then you don't get the performance. And in fact, I like this paper by Fisher, Josh Fisher, when he invented the very long instruction word architectures, which you saw, VLIW, and the enormously long instruction word with 512 bits. He basically wrote, to program a vector machine, the compiler or hand coder must make the data structures in the code fit nearly exactly the regular structure built into the hardware, basically the vector length. That's hard to do in the first place and just as hard to change. One tweak and the low-level code has to be rewritten by a very smart and dedicated programmer who knows the hardware and often the subtleties of the application area. Hopefully this will become a little bit more clear. How many of you program GPUs here? Okay, 1, 2, a few, basically. That's good. I mean, I didn't expect you to. I definitely didn't even program before coming to college, I would say. I guess I did in high school a little bit, but that was a long time ago. But GPU, if you do GPU programming, probably you will see that your performance is very sensitive to how you actually optimize your code, how you fit it into the vector registers, how you lay out your data inside memory, and we will see that. Okay, the second limitation, so I said only. Only is not true because you can actually make everything work. This is still a machine where you can execute any program, but you will not be able to efficiently. That's why only is in parentheses. It still works, but you don't get the best performance or efficiency out of it. Also, there's another limitation is memory bandwidth can easily become a bottleneck, especially you don't have good balance in terms of compute memory operation balance. So you bring an array only once and not do many things on it. You need to bring a lot of elements. You can imagine one operation, one instruction specifies, let's say, 1 million operations on 1 million different data elements, which means that your memory needs to supply those elements. Right? And we will see that. We will talk about in this lecture how the memory is designed to supply those elements. One way we've seen before is multi-porting the memory. Right? You actually have 1 million ports to memory. Doesn't sound very efficient, right? No, but that's one way of doing it. So we're going to see another way of doing it today. And if your data is not mapped appropriately, you may get conflicts. Okay, so let's go into a little bit more depth. This is what I drew on the piece of paper last time as a vector register, basically. Basically, each vector data register now holds n values instead of a single value. And m bit is basically how wide is your registers, right? This is a vector register. You basically have vector register 0, and it has n elements in it. So 64 could be a good n, for example. Another vector register, and you may have some number of vector registers. And we're going to add some control registers telling us how long are our vectors, vector length, what is the stride, what is the distance between the different elements in memory, not inside the registers, and what is the mask? We'll talk about mask. So masking is how you do conditional operations. Instead of doing branches, you do masking. Basically, the mask register is a register that has n elements in it, n 1-bit elements, and that bit specifies whether the vector operation should operate on the corresponding vector register elements. That way you can actually do, let's say, 64 additions. If all your masks are 1, that means that you're going to add 64 things. But if one of the mask bits of register, this entry 0 is 1, everything else is 0, you're still going to do the vector operation, but you're going to only have the first 2 elements added together, and everybody else will not be added because the mask is 0, meaning that you really shouldn't do the operation. That's how you can do conditional operations, and we'll talk about that. It's a pretty cool concept, and it's employed in GPUs today, for example. And it's also employed in other processors too, but we won't get into it. So maximum vector length can be n. This is the maximum number of elements stored in a vector register. That's good. Oh, okay, we've already talked about this. Vector mask register indicates which elements of vector to operate on. So this is one way of setting the vector mask. This is basically a single bit vector. If a vector register's entry is equal to 0, mask is set to 1. Otherwise, it's set to 0. Now, this way you can do conditional operations based on whether or not the data element is 0 or not. If it's 0, then you will do the next operation conditionally. We'll see an example. But let's look at the functional unit. So we know the registers now. And you can actually, this is the minimum set of things that you need in a vector machine. Vector functional units. So we've seen functional units before. They would operate on a single scalar register value, but now we have vectors. What we can do is we can pipeline the elements into the functional unit. So in this case, this is a 6-stage multiplication pipeline, as you can see. It takes vector register 1 as input, vector register 2 as input, and produces the result into vector register 3. So all of the elements are independent of each other. So in the first cycle, it takes element 0 from vector 1 and vector 2. In the next cycle, that moves to this stage, and element 1 gets fetched or dispatched into the functional unit. In the next cycle, element 0 moves to the next stage, element 1 moves to the next stage, and element 2 gets fetched, ... So you really have 6 elements, or 6 pairs of elements from vector 1 and vector 2 that are being multiplied, as long as you pipeline your multiplier. And at the end of the 6th cycle, you get the result of the first element stored into the destination vector's 0th element. And the next cycle, you get the result of the second element, or first element, like instead of 0th element, first element, second element, third element, ... So in consecutive cycles, you get consecutive elements. So in fact, if you want to keep this pipeline full, you can have a huge, like 64-stage multiplier, right? Because you know that they're all independent of each other. And that's how people built, for example, the earliest supercomputers. The Cray supercomputer had deep pipelines in its multiplier, which is the example over here. How many of you know that there is a Cray machine at ETH? Okay, and you visited it? So maybe that's a good task for the next lecture. You figure out where this Cray 1 machine, which is kind of this, of course it looks different. I should have taken a picture of it and put it over here. There's a Cray 1 machine in actually the cab building, right? And you can, actually it wasn't the cab building until recently. You can go and visit and look at it. It's not like this, it's huge. But basically, Cray 1 was built exactly the way I described it, and we're going to execute some code on Cray 1 in a little bit. If you look at this, you don't need to see all of this, but there are some vector registers, as you can see. There are 8 vector registers, and each of them have 64 elements. Each element is 64-bit wide, and this is 1970s. We'll see what memory banks are soon. But there's also a scalar portion of machine. It's actually a heterogeneous machine. It's not just purely vector. So this vector part was only this part. But there is also a scalar part, which is heavily pipelined. It was an in-order pipeline at the time. Basically, you see scalar registers and scalar functional units also. So if you were doing vector operations, SIMD operations, the instructions would go over here. If you were doing scalar operations, the instructions would go here. So it's really a heterogeneous machine. And you don't need to know about the things over here. So let's look at the memory system, because we need to fetch these vectors from memory into the registers, right? And we're going to fetch a lot of things. And I have this thing that's called memory banks over here, which you probably haven't heard of. And I have 16. So this 16 memory banks allow the fetch of 16 different things in parallel, but it gives you one by one, since it's a vector machine. And we will see that. So one option, if you want to fetch 16 elements at a time, you can have 16 different copies of memory. That's one solution, right? That sounds very bad, because you don't want to copy your memory 16 times. Expensive. Or you can have 16 ports into a single memory. 16 different addresses can be supplied, and you can get 16 different values. That's called a port. It's expensive. If you studied the lower level design, you will see that that's an expensive way of building circuits. You can think about it. Or you can have what's called memory banks, as we will see. So why do we need memory banks? Basically, we need to load and store vectors from memory or to memory, right? This requires loading and storing multiple elements. And elements are separated from each other by a constant distance called stride, as we've seen. We're going to assume stride is equal to 1 for now, but that's fine. Elements can be loaded in consecutive cycles if we can start the load of one element per cycle. Basically, we want the memory system in a vector machine to be, we want to be able to start one element every cycle. And every cycle, we want to be able to get one element from the memory system, right? That's what we want. And if we're doing a load of 64 elements, at the end of 64 cycles, we would have gotten the first element. Basically, where we would get one element per cycle, and it would take us 64 cycles to get all of the elements, right? Assuming the latency is 1. But the latency may be long. Basically, we can sustain a throughput of 1 element per cycle. So the question is, how do we achieve this with a memory that takes more than 1 cycle to access? If it takes 1 cycle to access an element, everything is good, right? It takes 1 cycle, so you get the first element, and then you supply the next address, you get the next element, you supply the next address, you get the next element, ... That sounds good. The problem is memory is usually more than 1 cycle to access. So what we do is we bank the memory. I mean, I've given you other solutions, but we're going to look at banking. And then interleave the elements across banks. So let me give you an example. So this is what a bank memory looks like. You have these different banks, in this case 16 banks. Each of them has a memory address register and a memory data register, but they have a shared data bus. And then there's a shared address bus. So every cycle to a given bank, you can send the address, it gets latched here, and the bank can start accessing. So after n number of cycles, it'll give the data into the memory data register, and you can get it back. Which means that in the next cycle, so let's say we send the first element here, base address. We give the address over here, and the next cycle, we give base plus stride here. In the next cycle, we give the base plus 2 times stride to get the next element. In the next cycle, we give the base plus 3 times stride, ... That way, we can start the fetch of 1 element every cycle. Because we know the stride, in this case, stride is 1. We know the base address, and we start the access of the first element in the first bank. While that's happening, we can start the access of the second element in the second bank. ... Now, your bank can take 10 cycles, and you'll be okay, right? Because you'll start the access of 10 elements in those 10 cycles, and in the next cycle, you will get the result from this element. And then in the next cycle, you get the result from this bank. In the next cycle, you get the result from this bank, ... So this is a very cheap way of enabling multiple memory accesses concurrently, because concurrently you're accessing multiple banks, but every cycle you're getting only 1 value. Basically, you have only 1 data bus over here. Does that make sense? Basically, we divide this memory into these, what is called the banks. You can access the banks independently, but they share the address and data buses. They share the address and data buses because these are expensive. So if you look at memory, basically you're going off the CPU chip over here. If you had 16 different buses, you need 16 times 64 bits. That's a lot of bits. That's like 1024, right? 2 to the 4 times 2 to the 6. 1024 bits. That means you need 1024 pins on your CPU. Now, today's CPUs have a lot of pins, but they don't use it for data, most of them. So 1024-bit pins is really expensive. Here, you can only have 64-bit data bus without requiring all of those 1024 pins, but you can still sustain a throughput of 1 element per cycle. Right? That's the idea. That's why they share the address and data buses. Right? That's why this is a much cheaper design than having many, many data buses to different banks over here. And as I said, you can start and complete 1 bank access per cycle, which means that you can sustain n parallel accesses, assuming if all n go to different banks. What if they go to the same bank? Well, that's my coffee shop. This is the coffee shop Tannenbar. I want to access it. And I supply my address, but the bank says, oh, I already have an address here. So I'm servicing somebody else. So if all of the accesses go to Tannenbar, you'll have bank conflicts. Whereas this other coffee shop, whose name I don't know over here, we'll call it the main building coffee shop, that happens to be empty, and my access happens to go there, then I can access it fast. So this works only if your accesses are nicely distributed across different banks, right? The first access goes here, the next access goes here, the next address happens to be here, the next address happens to be here. Now, in a vector machine, it's beautiful. If your stride is 1, you know that you can lay out your data such that the first elements are always here, the second element is here, third element is here, fourth element is here, ... And then 16th element is here, and then the 17th, or index 16 is over here, right? Basically, every 16th element is placed into this bank. and every 16, starting from 1, every 16th element is placed into this bank. Starting from 2, every 16th element is placed into this bank. Sounds beautiful, right? Is that clear? That way you eliminate the conflicts. Now the problem is you don't eliminate all conflicts, right? What if you're always what if your stride is 16 now? Now you're screwed. Because you always go to the bank 0. So that's exactly what Josh Fisher meant when he said this, basically. Basically, one tweak and the low-level code has to be rewritten. One tweak that changes your stride, either in the hardware or the software, then you need to rewrite your code such that you don't get those bank conflicts. This is a huge problem in GPUs, for example. GPUs, you want to eliminate these bank conflicts. You want to lay out your data such that the different operations access data in different banks at the same time. You can start one access per cycle. If you're conflicted on this bank, on Tannenbar, your performance tanks. Make sense? Okay, now we've started the memory. So this is actually one of the reasons why I wanted to cover GPUs, because it leads to a very good transition into memory. This is really where you need a high-performance memory system, whenever you're really pushing the boundaries of how many elements you want from this memory system. A single-access memory system is not doesn't need to be as high performance, although there are other reasons why it needs to be high performance because of latency reasons, right? But here, again, we're doing latency. We'll see that. Okay. So, okay, this is another look at the memory system. As I said, you have the base address, and you add the stride to it. And every cycle, you go through this loop until you finish the number of vector, the vector length. So next address is equal to previous address plus stride. So I'll give you this example. If stride is equal to 1, and the number of consecutive elements interleaved across banks, and number of banks is greater than bank latency, then you can sustain 1 element per cycle throughput. So, for example, if your bank latency is 5 cycles, and if your elements are 0th element is here, 1st element is here, 2nd element is here, 3rd element is here, 4th element is here, you start the access in the 1st cycle here, you get the data after 5 cycles, you can sustain 1 element per cycle throughput because all of your elements need to be accessed from consecutive locations. That's good. Right? Then you don't get any conflicts. But if your memory latency is, let's say, 17 cycles, here you have 16 banks, by the time you get the data for the 1st element, you do initiate the access for the 16th element, and you get a bank conflict over here. So if you want, so how many banks you want to add to your memory system depends on how long your memory access latency is in the bank. If your memory access, in this case, in Cray, for example, Cray 1, memory access latency was 11 cycles. That's why they had 16 banks. They could have had 11 banks, but now addressing 11 banks is hard because we're using binary numbers, right? So they had 16 banks, and at the end of the 11th cycle, they would get the results out of this bank for the 1st element. And at the end of the 12th cycle, they would get the result out of this bank from the for the 2nd element because they would have started the access in the next cycle. At the end of the 12th cycle, you would get this. The 13th cycle, you would get this. 14th, 15th, ... And you have enough banks if your stride is 1. Right? Now, if your stride is something else, then the problem becomes more complex. That's why it's good to have strides of 1. Right? Okay, so these are, for example, if I tell you, if your stride, if you have a memory access latency of, let's say, 33 cycles, how many banks do you need such that you can sustain 1 element per cycle? If your stride is 1, how many would you tell me? Your access latency is 33 cycles. We want 1 element per cycle throughput. Every cycle we want to get 1 element out of it. And our stride is 1. How many banks do I want there? Anybody? 64. Yes, you say 64? And you're absolutely right. Now, if you're a mathematician, the answer would have been 33. But you're an engineer. That's why you're here. That's why the answer is 64. Because you know the constraint. The constraint is you have binary numbers to address this. And the closest you need at least 60, basically, you can, if you have 32 banks, you know that you'll get a conflict, right, for one of the accesses, because your memory latency is 33. If you have 64 banks, you won't get a conflict. You would be wasting 31 of those banks, but that's okay. Now you're able to address them, because you can address them with binary numbers. Does that make sense? Okay, good. So this question becomes even more fun if you change the stride, of course, but maybe we'll have an interesting question on that. Okay, so let's look at the example that I was promising. So I'll give you this, maybe not so interesting code, but it exists in real programs. Basically, for 50 elements, we do this operation. Basically, we're averaging, this is element-wise averaging of two vectors. We're averaging A and B, and writing the results into the C. So let's take a look at the scalar code in some language, some assembly language. Basically, we move the counter, loop counter, 50, into R0. We move the base addresses of the arrays into these three registers. And then the first thing we do is, basically it's a loop. You need to loop through 50 times, and every time you need to do this operation. The first element in the loop loads A0 in this case, and then increments the base address. So there's this funny notation that I have over here, which some machines actually use. This is called auto-increment addressing. Basically, you load from memory address in R1, put the result into R4, and you automatically increment R1, such that you go to the next element. So actually, a lot of machines have that have this addressing scheme where you automatically increment the address one by one because of this behavior of programs. You basically go through a vector one by one, which is consecutively laid out in memory. And the second load basically loads from memory address R2, which is starting from the base address of this array B, and then it loads into R5, and then auto increments R2. And then third operation is basically this addition over here on the vector, the scalar elements that you just loaded. And then the next one is a division, which is a shift by one in this case. And then the next one is basically a store, which is very similar to this load, except you store into the base address starting with address C, and then store register 7, which is the result of this, and then auto increment. And then to do the loop condition, we have this interesting instruction here, which is decrement and branch if not 0. Basically, what this does is it decrements R0, which is our loop counter, and then checks if it is 0. If it's not 0, it goes back to the loop. If it is 0, then we're done with the addition. So it's a compact way of doing the branching, as you can see. And some machines have that. PowerPC actually has these weird instructions that look like this. It's fun, right? That's how you can design an instruction set. But if you look at this, this is interesting in several ways. A lot of these operations are dependent on each other. As you can see, within the loop, you have a huge dependency. If you look at this in a scalar code, these things are dependent on each other, right? A lot of them. Not all of them, though. We're going to look at the... and these are the latencies that I'm going to associate with them. 1 cycle for these moves. 11 cycle, which is the Cray latency for the load. 11 cycle for the other load. Add takes 4 cycles. Shift takes 1 cycle. Store takes 11 cycles. And this branch takes 2 cycles. So let's take a look at how long it takes to execute. First of all, how many dynamic instructions do you have here? 304, yeah, that's good. I'm sure you calculated it. But it's not that hard to calculate. You 1, 2, 3, 4, 5, 6 here. 6 times, 50 times you iterate. That's 300, and then 304 to set up the loop. Okay. Well, I've given you the answers. That's okay. You can do it by yourself. But basically, scalar execution time on an in-order processor with 1 bank. It turns out, if you have only 1 bank, and it takes 11 cycles to access memory, you'll take 11 cycles to access this. In the next cycle, you'll start the access. You'll take 11 cycles to do this. After you get the data, you'll take 4 cycles here, 1 cycle here, 11 cycles here, 2 cycles. So you add up all of these because these are dependent instructions. Everything is dependent, as you can see over here, right? And also it depends on your pipeline depth, but I'm going to assume that. Basically, you add up this 33, 37, 39, 40. 40 times 50 is 2000 and 2004. That's 2004 cycles. Now, I'm assumed in a pipeline processor where how do you predict this branch? I've assumed you predicted not taken. If you predicted taken, you'll come up with a different result than 2004. Because taken is a good prediction actually in this case. But let's predict it not taken for now. Okay, so that's the problem with having one bank basically. If you have one bank, you cannot start this load while you're doing this load. Because you have this is actually accessing memory for 11 cycles. Right? Now, if you have 2 banks, 16 banks, let's say, let's do 16 banks. What we can do is we can, when we store the consecutive words in consecutive banks, with the first 2 loads in the loop can be pipelined. Basically, you start the first load in the first cycle. At the end of the 11th cycle, you get the element. You start the second load over here in the second cycle. At the end of the 12th cycle, you get the result. So it takes 12 cycles to finish these 2 loads, 4 more cycles to do the add, 16, 1 more cycle to do the shift, 17, 11 more cycles to do the store, 28, 2 more cycles over here, 30. 30 times 50, assuming not taken branch prediction, is 1500, and then 4 cycles over here. So you reduced it 1500, 4 cycles, by just increasing the memory banks to 16. Actually, you didn't need to increase it to 16. You could have had only 2, right? Because in this case, we're doing 2 loads in parallel, pipelined. This is scalar code. The first load you can start. The second load you can start in the next cycle. And, okay. So you just learned that banking the memory helps in a pipeline processor also, right? Because this load now can start, the second load now can start its access instead of waiting for 11 cycles. So banking is a general concept that helps whenever you need to do multiple accesses to a memory. But we'll see that it's much more powerful in the vector machine. So that's good, 1500 4 cycles. You may think that that's good. Why 16 banks? We've already discussed this, because 11 cycle memory access latency. But in this case, you really didn't need 16 banks, because we're really doing 2 loads per cycle. Now, if your branch prediction was something different, if you predicted it correctly, then you would be doing more loads. Then that gets interesting, right? You do need more banks in that case. That's why out of order and pipelined machines actually need that as well. Okay, but we're assuming in order processors over here, which means that you're stalling at dependencies, right? True data dependencies. That's why you cannot pipeline this add with this load. You cannot pipeline this shift with this add. You cannot pipeline ... because they're all dependent on each other. Okay, so let's look at the vectorizable version of this code. It looks much simpler, if you will. Basically, what is a vectorizable, first of all? A loop is vectorizable if each iteration is independent of any other. It's also called parallelizable, but I like vectorizable. But basically, in this case, iteration 0 is independent of iteration 1, is independent of iteration 2, ... Because the induction variable is really the iteration counter, and there is no funny things that you do over here. You don't say ci equals I plus 1, for example. Now the iterations are dependent on each other, right? Could be. Well, if you say ci plus 1 equals ai plus bi divided by 2, now iterations could be dependent on each other. Anyway, we're not going to talk about that. So how do you vectorize it? First of all, we need to know our vector length, right? Vector length is 50 in this case, because we know that we're going to operate on 2 vector elements that are of 50 elements each. Vector stride is 1. We're going to assume that vectors are laid out that way. This is the first instruction. You load vector A into vector register 0, and this is its latency. It takes 11 cycles to get the first element, and then we want 49 other elements after that, or vector length minus 1 elements after that. So this instruction really takes 11 plus vector length minus 1 cycles. The second instruction loads vector B into the vector register 1, same latency. The next instruction does an add of vector 0 to vector 1 into vector 2. Its latency is the first element addition finishes after 4 cycles, and then you want 49 other elements finishing, and it's pipelined, right? So 4 plus vector length minus 1. The next instruction is a shift. It takes the result of this add, shifts it by 1, puts the result into V3, and it takes this long. And the last instruction is a vector store, right? And that basically takes the result of the shift, puts it into, stores it into C, and takes 11 plus vector length minus 1 cycles. Now, the first thing you notice over here is there's no branch. branch is gone. That weird decrement B and Z is gone. Because our vector length is smaller than what the machine supports, and we can code this entirely with sequential instructions, SIMD instructions. The second thing you would notice, now I'm going to ask you, how many dynamic instructions are here that you fetch?
285.
Wait, 285 is what? Number of cycles?
Yes.
That's not what I'm asking. You're correct, which is good, but that's not what I'm asking. That's the answer to the wrong question, but a correct answer to some other question. How many dynamic instructions we fetch? Just 7, exactly. Basically 1, 2, 3, 4, 5, 6, 7. That's it. If you go back, we had fetched 304 dynamic instructions and wasted energy fetching every single one of them. Now we fetch only 7 and we accomplish the same work. That's where the energy efficiency benefit comes from. Now let's see where the performance comes from and how we will get to 285. So, okay, we're going to assume no chaining. We're going to see chaining. Chaining is a fancy word that was developed in vector machines. This is basically data forwarding. You forward one data element from one vector functional unit to another vector functional unit, or the beginning of the same functional unit, if you want to make it complicated. We're going to assume no data forwarding to begin with. Okay. So the entire, in this case, if you don't have data forwarding, the entire vector register needs to be ready before any element of it can be used as part of another operation. So you need to finish the entire load to be able to do the add. Now this is very similar to no data forwarding in the scalar pipeline, right? But in the vector pipeline, there is really no reason to do it, because once you finish the first element, first pair of elements, load, you can now send it to the add unit and do the add, right? So it's a lot, forwarding is very powerful in a vector machine because all of the data elements are independent in a vector. But we're going to assume the bad case here. No chaining, no. So we're going to assume one memory port, one address generator, and we're going to assume 16 memory banks. We're going to interleave consecutive words, consecutive elements in consecutive banks. And this is your result. Basically, this is your what you do, I think. Is that correct? Okay, yeah. Basically, these two takes 2 cycles consecutively. Now, one memory port, which means that we can start the load in one cycle, in the first cycle, and then we can start the next element in the same load in the next cycle, next element in the next cycle, next element in the next cycle. The first element will return after 11 cycles, and the next element returns after 49, right? Basically, the load takes 60 cycles, as we predicted over here. Right? 11 plus vector length minus 1. That's the first load over here. Then you start the next load. You can start the next load only after this because we have only one memory port. If we had another port to each bank, then we could have actually started this load also here. But we're going to see that next. Okay, this takes 60 cycles. The add, only after the loads, all of the elements of the load finishes, we can start the add. Because remember, we don't have data forwarding. So it takes 4 cycles and then 49 more for the consecutive elements. And only after all of the elements finish, we can start the shift. And then it takes 50 cycles total, 1 plus 49. And then only after the shift finishes, we start the store. And that's where your 285 comes from. So even with this, we have just 285 cycles. Compare this to 1504. That's a huge improvement, right? And we're not only improving performance, we're also improving efficiency because we're fetching much fewer instructions. We're doing the same number of operations, but the amount of control that you do, the instruction fetch that you do, is reduced significantly. Okay, so can we do better? It's always a question to ask. Well, I have a lot of assumptions over here. Let's break some of them and make the machine a little bit more complicated. So the idea is vector chaining. You've seen the idea. Forward the data from one vector functional unit to another. Instead of waiting this load to finish all of its elements, when the first element finishes, forward it to whatever is needing it, right? And it's very simple. It looks like this, basically. Basically, the forwarding path, bypass path, right? Of course, this is pictorial. In hardware, when you design the RTL, you need to do it correctly, right? That's the idea. And you can do the chaining. So it's really a network of chaining, network of forwarding network. In fact, if you remember the machines that we see, they called it the bypass network, right? Because you need to chain between different. This multiplier needs to be able to feed into load, maybe. I'm not sure. But multiplier may need to feed add, and add may need to feed into the multiplier also. That's how things get complicated. Okay, we're going to assume that, and let's take a look at our code. Well, this is going to improve our performance. So these are the two things, and then we have one memory port. So this is the first vector load, if you remember. It takes 11 cycles plus 49 to finish all of the elements. And then we start the next load. Now, once we have element 0 from the first load and element 0 from the second load, which happens at the end of this 11th cycle, we can start the add, right? I should have marked these load and add, but you remember the code. No, I have the code over here. Basically, vector load, vector add. And you have both elements over here. Maybe just to jog your memory, I'll just show the... Basically, we're doing this, AI plus BI. We've loaded both A0 and B0 at that moment. Now we can start the add, because we've forwarded the data from the load unit to the add unit. Now add can be pipelined with the load of the remaining 49 elements of the second load. And every cycle we get another element, we forward it to the add unit. So every cycle we start another add operation. Every cycle we get the element from the second load unit. We take that element, we take the element from here that we've already loaded, we send it to the add unit, and now we can overlap the latency of this load with the add. So let's finish this. Basically, this add completes this way. So you do the first add finishes after 4 cycles from the end of this load. And now we can start the shift. You forward the data value from that add to the shift. It takes 4 cycles. It takes 1 cycle here, and then you keep forwarding the elements. Now shift latency is overlapped with the add latency because they're both pipelined. Now you can say this load finishes. Now we can start the load of a store. You can say, oh, why don't I start the store over here? Because I have the results over here, right? Remember what we were doing is we want to store into C. We've done the add, we've done the divide, which is the shift, and we have the result of the shifter, right here actually. But we cannot put it into memory because memory is busy doing this load still. It's still loading, I don't know, some number element you can compute actually. It's loading 50 elements, and until it finishes all of the elements, you cannot store the store because we assumed 1 port to memory. So the store can start only here. So it starts, and it takes 11 cycles plus 49. So you've overlapped a lot of latency. It's beautiful. Now it's 182 cycles. So 285, 182. Let me finish this example, and then I'll give you a break that's shifted, if that's okay. Unless somebody really needs to have a break. Who really needs to have a break? Okay, let's have a break then. Okay, let's continue. So now you know how we got this code from 1504 cycles to 182 cycles, right? So the question again to ask is, can we do better? And the answer turns out to be yes. So where are the cases where this code is not doing well? For example, this load and this load. There's really no dependence that these loads have on each other, right? One is loading from array A and the other is loading from array B. And we don't have anything dependent, assuming that array A and B, again, even if these are reads, right? There's no dependence. As long as one is not writing to the array, but there's no writing also happening, this is really a load. So these loads are actually independent of each other completely. The reason this load is starting after this load is finishing is there's only 1 port to memory, 1 address generator that we assumed. And each bank can be accessed with only 1 address generator. So we cannot pipeline these 2 loads. But if we have more resources, if we duplicated the memory, if we added more ports, we could have pipelined them, right? So we're going to do that. And this load and this store can also not be pipelined, as you can see. While this load is going on, the store cannot start. That's why, even though we had the result over here, we couldn't operate on it we couldn't store it until this load finished. Again, the assumption we had was each memory bank has a single port. If we had 2 ports, meaning if we would start the load of address A0 in the first cycle, and then A1 in the next cycle, but also B0 in the next cycle, and then A2 in the next cycle, but also B1 in the next cycle, we could pipeline these two loads, right? For that, you need to be able to have a multi-ported memory. So let's go back to this banking that we had. It's not to be confused. It's a bank, basically. So remember, we had bank 0, bank 1. You can see it, right? Yes. And then bank 15. So we had one address generator, which takes a base address and then adds to it the stride. And then the result goes into the address bus. And the address bus, of course, you select the right appropriate bank. So let's go into a little bit more detail as to how this works. So let's assume that we've laid out such that A0 is here, A1 is here. So somebody needs to do that data layout, which is usually the programmer or the compiler. A16 is here, A17 is here, ... A31 is here. Now you've laid out your data nicely. 32 is here, ... You start with address A. Oh, that's not here. Address A. In the first cycle, you basically supply address A, which means that you go to A0. And there needs to be logic that determines that this maps to bank 0. And how do you do that? Let's say you have a 32-bit address. Let's say this is word addressable to make life easier. Whenever you address it, you get one word out of memory. How do you determine which bank you access? So this is bits 0 through 31. If you have 16 banks, the bottom 4 bits over here, bits 0 through 3, determine which bank the address is at, right? So basically, you need 4 bits to specify the address. Okay, so for the base address over here, you'll have 0, 0, 0, 0. So there's control logic that takes you to bank 0, and you start the access from address 0. So you need to have an address port over here, a single port. That enables you to keep accessing it. In the next cycle, you get the stride, you add it to the base, and then start the next access. Basically, the next address you get will be A+1 in terms of word address. So you really load A1, and the address will be incremented by 1. So your bank will be 1. So the next cycle, you start the address from this bank. Now, if you have one address port. If the next cycle, you start basically. So if you add another load, you basically need another one of these, right? Base. Of course, it's going to be more expensive. And your base will be B. After you start address 0, you will be able to start B0 access by having another port, which means you another address bus, right? And then another address port over here. Second, this is the first address port, this is the second address port. Let's call them read ports. So in the first cycle, you start the load of this address. Let's look at the execution timeline. You were loading array A. In the first cycle, we start the load of address A0. In the next cycle, A1. While we're starting in the next cycle A1, we're going to start B0. Right? Doesn't look that good, but in the next cycle, we're going to start B0. And the reason we're able to do that is because we have another address generator, which is linked to another address port in each bank. And every cycle, you generate one address and send it to the consecutive banks. Does that make sense? That enables you to do 2 accesses in parallel. You start the first access for address A0 over here. In the next cycle, you start B0. Now, after 11 cycles, you get A0 over here. And after 11 cycles over here, which is 1 cycle after this, you get B0. Now you can operate on them, right? Make sense? Right. Okay. Now you need more data buses also, right? That kind of sucks. But you do. That's why doing this multi-porting is complicated, as you can see. Right? It's not as simple. So your cost increases in the end. Because you need to be able to get A0 here, A1 here, but at the same cycle you're getting A1, you're also getting B0. Right? So you need multiple data buses. Well, in this case, 2 data buses, that's good. If you want to sustain 2 ports, you need 2 data buses. Right? Okay, basically at the end of 11 plus 49 cycles, we get all of the elements of A up to A49. And then one more cycle after that, we get all of the elements B, B49. Now we can start the next operation. Basically, we pipelined accesses to array A and array B this way by adding more hardware, more ports, more address generators, as you can see. So hopefully this clarifies the concept of banking also. Basically, this shows you how important it is to lay out your data. If you're accessing A0, A1, A2, A3 this way, it's important to lay them out to different banks. But if you're accessing A0 first, A16 next, if your stride is 16, they're all mapped to here. So you won't be able to have this nice picture where you get 1 element per cycle. Okay, so let's keep going. Yes?
My vector A has 16 elements, right?
Your vector A, well, in this case, in the picture that we had, has 50 elements, right? We do 50 element iteration. So basically, you would lay it out continuously, right? This is A36 over here. I guess in this case, it'll be A52, or is that correct? No, 48. Could you say it again? Where exactly what comes from?
11 plus 49 cycles.
Oh, so it takes 11 cycles to access 1 element from 1 bank. That's the assumption. You start the access at time 0. At the end of the t equals 11. Actually, yeah, basically at the end of t1, you don't get anything. But at the end of t equals 11, you get the first element. So each of these takes 11 cycles to access. And the first element comes after 11 cycles. The second element comes 11 plus 1 cycles from this bank. The next element comes from this bank. 1 more cycle later. The next element comes 1 more cycle later from the next bank. So you get 49 more elements. That's where the 49 comes from. Okay? Good. Okay, so let's go back to this picture. We had this assumption, and based on this assumption, we got this performance because we weren't able to pipeline these loads and pipeline the store with this load. As a result, we got 182 cycles. So if we had this multiple ports that I showed you over here, life would be better, although maybe I should switch here. Cycles. But basically, life would look like this. Now you're able to start the load of vector B 1 cycle after. You start the load of vector A because you have 2 address ports and 2 data ports. Now these loads are completely pipelined, as you can see. Now, because we have vector forwarding or chaining, you get both data elements at the end of this cycle for A0 and B0. Now you can start the add, as we've seen. Now you can start the shift after 4 cycles. Now you can start the store. You can start the store here, even if it overlaps with this load, because I'm assuming in 1 store port also. So not only am I assuming I have 2 address ports, 2 ports to load from. It's called a read port. Basically, not only these 2 read ports, but I'm also assuming I have 1 write port over here. So while I'm doing 2 reads, I can also do 1 write. Now it's more expensive, which means that you need to have another address generator over here, another address bus, but now you're able to do writes into memory. So it's more expensive. But as you can see, we're able to perfectly pipeline this store with that load over here, which we were not able to previously do. And that gets us to 79 cycles only, which is almost a 19x performance improvement compared to 1504 cycles, right? Which is a lot, actually. Now we have more hardware. You could argue about that. What if you add the same hardware to the other code? Actually, you wouldn't get anything. You would need to add some other hardware to be able to get the independent instructions, like out-of-order execution. But this is still reasonably simple hardware with a relatively complicated memory system now, right? You don't do only 1 access per cycle. But it's still a lot. Okay, any questions? this. So now you see the power of the machine, if you will. And if you can do better than this, it'd be good to know. But it's hard to do better than this unless you go to some other, because this is dependent code. Now you should be able to load multiple elements per cycle from a vector, which is a different topic. Okay, so there are a number of questions that you may ask. Okay, this is nice, but what if my number of data elements is greater than the number of elements in a vector register? So I'm adding arrays of length 1,000,000, and my vector register has only 64 elements. Well, now you add a loop, basically. You basically break the loop so that each iteration operates on number of elements in a vector register. For example, if you have 512 data elements and 64 element vector registers, you do 8 iterations of what I just shown you, that loop over there, where vector length is 64. At the end of the 8th iteration, you change the vector length to 15, because there's only 15 more elements that are remaining, and you do 1 iteration that way. Basically, you code a loop. That's why vector machines need to have branches also. So you need to change the value of vector length. Now, when you change the value of vector length, it's disruptive, because vector length is used by all of the instructions that were previously in the machine. So you need to ensure that no one gets the wrong vector length. This is, again, a data dependence. It's just another register, right? Okay, so this is called vector strip mining. You don't need to know exactly what it is, but basically it's looping. So what if vector data is not stored in a strided fashion? Let's make it more complicated. What if my memory accesses are not nicely strided? Stride 1 is good, as you've seen, but stride 10 is also good because you can predict the address. But there are many cases where we operate on data elements that are not as nicely laid out. So the idea to fix this, as I'll show you, is you use indirection to combine or pack elements into vector registers. Right. I'll give you one example of this. This is called scatter-gather operations, basically. You can scatter the data into memory to different locations, or you can gather the data from completely different locations as long as you supply a base address. Now, why would this be interesting? For example, if you want to vectorize loops that look like this, somehow, indirect addresses. Have you ever programmed this way? You have this indirection array. This basically specifies which locations in the matrix have interesting values, and the vector have interesting values. Let me give you an example. I need to switch to. So why would this be interesting, first of all? Let's say you have a vector, and for some reason, almost all of it is zeros. And you're not interested in the zeros. You have a 5 here, you have 85 here, and you have, I don't know, 32 here, and everything else happens to be zeros. This is called a sparse vector. The interesting information is not zeros, and they're only in 1, 2, 3. Did I miss something? I guess 3 locations, yeah. You have a 1,000,000 element vector, and only 3 locations encode good data. So what you do is, when you write out this data, you write it into an index register and say, I have an index vector. If I'm going to access this vector, I don't know, in this case it was C, I think, C vector, I'm going to index it with this D register. And D register will tell me the indices starting from address C, which contain the interesting elements. Now, what are those indices? Let's say this is the 0th element, and this happens to be, I don't know, 1,000th first element. So the first interesting element happens at 1,004. Right. The second one happens at 1,285. That's the location that happens to be. And the third interesting happens, I don't know, 1,288, 87, just to make it interesting. Basically, I have 3 interesting elements, and the indices are here. Now, I can have this D element over here, and whenever I want to access the interesting elements over here, what I do is I go like this. Right? Basically, D tells me the index of the location that contains interesting data. I first access that, and then add to it the base address of C. So basically, I access element C plus 1001 in this case. When I is equal to 1, I access C plus 1285. When I is equal to 2, I access C plus 1287. And the data elements I load are exactly these. That way I get to skip doing the operation on the entire million element vector, because everything else is not interesting, right? Somehow, let's say I sampled the data from some sensor, and I know that zeros are not interesting in that sensor, but I figured out when I was sampling the data, the interesting parts are this. And when I'm processing the data later on, I go back and I only focus on the interesting parts. That way I can do only 3 loads, as you can see, right? As opposed to doing a million loads. So this is called a sparse vector, and this is called the index vector. And you use the index vector to get to the interesting elements in a sparse vector. So how do you do that in a vector machine? Vector machines have to do this kind of gather-scatter operations. Basically, that's exactly what I've shown over here. You're operating only on the interesting elements over here. I is much smaller, basically. So you do need an indexed load instruction. This is called a gather. First, you do need to load the indices, interesting entities in this D vector that I showed you over here. Somebody needs to do that. And then you do need to do a load indirect from this base of the register C, if you will. So basically, you load into vector register C this indirect address. So exactly what I showed you over here, but in a vector mode. We'll see another example of this. Basically, your base is the register that contains this address. You add to it all of these different indices, and you do a vector load. So this is a vector of 3 elements, right, where I is 3, because you have only 3 interesting elements, indices here. If this was 64 interesting ones, then you would have 64 different indices to 64 different locations over here. Okay, and then you load the B vector and then add to it B plus C, just like we've done before. Do the add and then store the result. So let's take a look at this. Basically, as I showed you, it's this implemented to handle sparse vectors, sparse matrices. They use an index vector, which is added to the base register to generate the address. So index, in this case, another example. And in this case, we're going to do a scatter, if you will. We have this index vector. The interesting elements we're going to store to an array. The interesting elements we're going to store will be element 0 at index 0, element at index 2, element at index 6, element at index 7. And this is the data we're going to store. We're not going to store it in consecutive locations. We're not going to store it in strided locations. We're going to store in indices at these locations. So what does the store, how do we do the store? Basically, you have a scatter operation. What scatter does, it takes the base address of this vector, takes the first element in the index vector, adds to it, compute the address, takes the first data element, and places it there. And then it goes to the next element in the index vector, takes the base address, adds to it the index vector, base plus 2, and stores this data element at base plus 2. Next element takes the base address, add to it 6, which is whatever is located in this next element in the index vector, store at that location the same element, the same location in the data vector. So base plus 6 gets 71.2. And go to the next element in the index vector, base plus 7 gets 2.71. And the rest of the memory you don't touch. Basically, we don't store anything to the other parts of memory because these are the only interesting locations in the array that we're going to modify. That's how you can modify arbitrary locations in memory, right? Instead of just strided locations. In this case, the arbitrary locations happen to be at base address plus 0, plus 2, plus 6, plus 7. But you could generalize it to any locations in memory starting from a base address. Now, of course, this is not as beautiful, perhaps, because now your address calculation is not a simple base plus stride, base plus stride times the element, right? But now your address calculation is base plus the index, where your index is obtained from another register, vector register. It's basically base plus index register I, right? Okay? So it's a pretty simple concept, hopefully. But this is employed, for example, if you program with Intel's AVX, advanced vector extensions, you will see that there are gather-scatter operations there. Is this clear? Okay, cool. Okay, so what about conditional operations? Let's make this an even more interesting machine. We've already talked about the mask register, right? So what if some operations should not be executed on a vector based on some dynamically determined condition? An example is this, for example. It's pretty simple. Well, maybe I don't need that loop over here, but it's a for loop. It's loops n times. Basically, if AI is not equal to 0, then you store into BI AI times BI. So it's conditional. Now you need to implement conditional operations, and the idea we've seen before is masking, right? Basically, you have this vector mask register. It's a bit mask determining which data element should not be acted upon, right? In this case, we load vector A into V0, vector B into V1. Now we need to decide which elements we should perform this operation on. Which elements should we multiply, and which elements we should store the result of the multiply to. So vector mask is set based on the condition that V0 is not equal to 0, meaning AI is not equal to 0. So for each element in A up to vector length, this operation basically sets a bit after checking this condition. Does that make sense? You do that for each element. In the end, the result is a vector mask register in a vector machine. Of course, you can have many of these, but let's say this is your vector mask register. 0 through, let's say you have 64 elements. Basically, it's a bit mask. What that operation that I showed you does is it checks whether vector 0 is not equal to 0, right? And we set the vector mask based on that. So you have another vector register, vector 0, which is wider. 0th element, 63rd element. This is vector 0. You basically, what this operation does is, we mask equals vector 0 is not equal to 0. You take each element of vector 0, you check if it is equal to 0, you send it to a functional unit. Now, if it's equal to 0, if it's not equal to 0, you set this bit to 1. And then you go to the next element, do it for elements. Now, if, let's say, most of this is zeros, but the last one is a 56. And I drew it longer because it's 64 bits wide, right? Last one is not 0, for example. The result of this operation would be, we're checking if vector 0 element is not equal to 0. In this case, it is equal to 0, right? So you get all zeros, right? Because the condition is not true except for this one. Only in this case, this Boolean equation is true. This element is not equal to 0, so you set this to 1. Make sense? Now, this may be basically, if you're going to use this for the equation that I showed you over here, now you really need to do only. Let's go back. Yeah, we were checking this. And we need to do the multiply only really on that particular location that's not 0, right? Oh, you cannot see it. And in that particular example, I showed you that only the last element is not 0. So what this multiply, the way it will operate is, what we're doing is really multiplying V0 times V1, right? And storing the result somewhere. Somewhere is V1 over here. Vector multiply. So the way with this vector multiply will operate is, well, it will take vector 0 and vector 1. This is vector 1. And basically, it's a masked multiply because our mask register is set to all zeros except for one location. What it will do semantically is it will not do the multiply for any of these elements, but it will do the multiply for only the elements where the mask is set to 1. So the result will be, you don't do anything over here. You keep this part of vector register 1 intact. but this part of the vector register will be 56 times whatever this was, whatever this value was, 56 times the previous value of V1 at location 63. Basically, you do only the masked operation. Only the element that at a mask bit set to 1 will be operated on. Okay? So it's very powerful. So how do you implement this? Is another question. Yes, so this multiply is operating only on the elements whose mask bits are set to 1. It could be 0 elements, right? It might happen that this is none of the elements are not 0. All of the elements are 0. As a result, this multiply will essentially be a no-op. It won't change anything. Right? And then you do the store. Store also operates on the mask operations. So you can think of this as, initially, if you don't change the mask, everything, all of the bits in the mask register are set to 1. All of the elements will be operated on. Now, if you change the mask, some of the bits may become 0, and those bits specify the elements that are not going to be operated on by the remaining instructions that come. And then you may change the mask again later. Okay, so this is actually a very general concept. It's also called predicated execution. Basically, execution is predicated on the mask bit. If the mask bit is true, you do execution. If the mask bit is not true, if it's 0, you don't do the execution. It's called predicated execution because you have a predicate. Predicate is that bit, right? If you operate only if that predicate is true. So if you hear this term, which actually exists in many processors today, ARM, for example, called it conditional execution. You conditionally execute some instructions, except you don't do it in a vector manner, you do it in a scalar manner. Even in the scalar domain, you can have this mask bit that says, oh, if this mask is true, execute the operation. Otherwise, don't execute the operation. That way you can eliminate the branches. In this case, we eliminated the branches, right? You could have had a branch over here in the vector machine, which is a horrible thing to do. But now, there is no branch in the machine, right? It's really branching over here. But the branch is gone. Instead, we have a vector mask that says if the data value in this register, mask register, is 0, do the operation. Otherwise, don't do the operation. So it's very fundamental, actually. What we've done is essentially, this is, if you look at this is a control flow, right? We've converted that control flow of dependency. This operation is dependent on the outcome of this branch. Here, there's no branch. We've converted that branch into a data dependency. Now, the operation is dependent on the outcome of this data that's produced by this mask operation. And the data is a bit saying whether you should do the operation or not. So it's a very fundamental concept. It's independent of vectors, vector machines. You can convert a control dependency into a data dependency this way and eliminate the branch. Okay. So let's look at one more example of this. It's another fun example. You can actually go crazy with it. You can do any kind of masking operations. And we will see how GPUs do it. So I'm showing you right now here, the way it's done right now, this way is you do it via programming, right? GPUs do it underneath. Underneath, they do this kind of execution. So basically, if you want to execute this code in a vector machine, you first compare A and B, vectors A and B, to get the VMask. And then that VMask, based on that VMask, you do a vector mask store of A into C. Now there's an else part of it over here. So the first VMask stores all of the elements, assuming that the element is in the A is greater than the element in the B into C. Now you need to do this else part of the code. What do? You complement the VMask. Right? You've already calculated this mask bit depending on this condition. Now these conditions, for the elements where this condition is true, you do this operation. That's this mask store of A into C. For the elements where the condition is not true, which means that you complement, that's a not of the vector mask register, you do a mask store of B into C. And then you set back the mask register to all ones at the end once you're done with this operation. So it's pretty simple. Well, and this is one example over here. Basically, if A and B look like this in memory, your vector mask would look like this, because we're comparing if AI is greater than or equal to BI over here. Now, you can look at this example on your own. So how do you implement these instructions? Now, if you go into the hardware design of it, there are two ways of implementing it. One is this, basically simple implementation. You have the 64-element register, and you have 1 bit for each of the elements. Yes? Oh, how do you operate on VMask, basically? Yeah, that's right. So that goes into more complicated things. You're thinking deeply. For the example that I assumed, we're not manipulating VMask in any other way. But actually, that becomes an issue. And so how do you mask the masked operations, right? If you want to generate much more complicated predicates, you operate on the VMask register as well. But let's not go into that over here. So that turns out to be an issue in the predicated machines. If you have questions, let me know afterwards, though. Okay, so how do you implement this? Basically, one way of implementing this is you execute all of the 64 operations, but then if the mask bit is 0, you discard the value. That's an energy inefficient way of implementing it, right? Basically, you see this is one way of it. Basically, we have this array A and B. We're adding element by element, putting the results into the C. And then we have the mask bit vector for each element, as you can see, mask 0, mask 1, ... And after we produce the results, we check the mask bit, and mask bit is our write enable into the destination register element. Sounds good, right? It could work. It works, actually. So you write disable if the mask bit is 0. If the mask bit is 1, that's good. So if almost all of your mask bits are 1, maybe this is not a bad idea. But if your mask bits, you have 64 entry register, and one of your mask bits is only 1, only one of your mask bits is 1, then you're doing 63 operations useless, right? So there's another implementation which is called the density time implementation. Basically, you have some logic over here that basically goes and scans the mask bit. And you only fetch from those vector register elements that you need to operate on. So there's some logic, additional logic, that goes through and says, oh, I'm going to operate on element 1, element 4, element 5, element 7, and I'm going to fetch only from those locations in the registers. And only do those operations, be frugal about it. Now, which one is better? Depends on how you do the scan implementation over here, right? Depends on how you can fetch from your vector register. Sometimes if you're always operating on all of the elements in your vector register, you can actually do a FIFO queue, right? You basically stream through your vector registers. Here you need to be able to fetch from different locations in your vector register now. So it's a trade-off again. So there are multiple trade-offs. And also it depends on how many bits are set in your mask bit as well. But you cannot maybe think about that when you design the hardware. That may be difficult to predict. Okay, let's talk about some more issues. So stride and banking. Let's go back to the stride and banking because it's really important. I'll be a mathematician over here. Know that you're not a mathematician, maybe. Maybe you are, but that's okay. So this is a difficult problem, actually. As long as stride and banking are relatively prime. Do you guys know this term? Relatively prime? Yeah. Okay, good. So basically, they're not divisible with each other, right? 3 and 5, for example, are good. Yeah, to each other. And there are enough banks to cover the bank access latency. We can sustain 1 element per cycle throughput. I'll let you think about this a little bit. So 2 and 16, for example, are not relatively prime, right? 4 and 16 are not relatively prime. If your stride is 4 and you have 16 banks, some elements, if your stride is 16 and 16 are definitely not relatively prime, for example, right? If your stride is 16 and you have 16 banks, all of the accesses will go to the same bank. So when you're designing these machines, you'd like to try to make things relatively prime. Relatively prime is difficult when you have an even number of banks. That's one of the problems. Storage of a matrix, we covered this actually early on. So now how you store your data very much dictates your performance. So row major order, we've discussed this earlier. Consecutive elements in a row are laid out consecutively in memory. In fact, I may have the picture over here, but I don't. Oh, I do have it. But I'll have another picture over here. Column major order, consecutive elements in a column are laid out consecutively in memory. So the problem is sometimes you may access a matrix in row major order. Sometimes you may access it in column major order, right? And you need to change the stride when accessing a row versus column. And one stride may be nice, one stride may be 1, but the other stride may be 16. So now you have a problem. You access the same matrix at different times with different strides. One stride is nice because it's relatively prime to the number of banks that you have, but the other stride is not relatively prime, so you get bank conflicts. And this is a very fundamental problem. How you lay out your data significantly determines your memory throughput, how many data elements you get from your memory, but then your access pattern also determines your memory throughput. So remember this picture that I had in a different way. We have this matrix multiplication. We're multiplying matrix A with B. And if we're doing this matrix load of A into vector register 1, basically we want to load this row into vector register 1, and we want to load this column into vector register 1. Now this is nice because your stride is 1. Consecutive elements of array A, or the first row of matrix A, are in consecutive locations. But you also need to load this column into another vector register so that you can do bitwise, you can get the dot product of the two vectors, right? The problem is this B is not stored as nicely. It's stored such that the stride is 10. And 10 is not relatively prime with 16. As a result, when you're loading this column, you get a lot of bank conflicts. So the load of this matrix will be really slow, even though the load of this matrix is really fast. That's why you can get significant performance degradation. So how do you minimize these bank conflicts? You can have more banks. 1 million banks, right? That helps. That's good. Or better data layout to match the access pattern. Now, this is the difficulty of programming. That's why GPUs, if you know the access pattern of your program, lay out your data nicely such that consecutive elements in terms of your stride are in different banks. You need to know the details of the machine. If you go back to that quote, now you need to know how many banks you have in the machine. And this may not always be possible. That's the problem, right? So I show you over here. Okay, maybe you lay it out in some other order. So this matrix, you lay it out in row major, but you lay this out in column major order. Consecutive elements in a column are in consecutive locations. If you do that, you get rid of the 10 stride. Now your strides over here become 1. Right? Remember, this is laid out in row major order. Consecutive elements in the rows are in consecutive locations. But here this is also row major, but you're accessing in column major order. So your access pattern is completely opposite of the layout. So you can change the layout such that it's the same as your access pattern. That's good. You fix this problem. But what if later you access this matrix in row major order? Now you have the same stride problem in a different time. So it's very difficult to match your access pattern to the data layout and vice versa, because you usually access the data structures in many different ways in a program. And another possible thing is you do a better mapping of address to bank. You don't take the last address bits, as I showed you earlier, 4 bits, remember, at the bottom, but you randomize them such that you minimize the possibility of bank conflicts. Actually, a lot of processors, memory controllers do this today to minimize the possibility of bank conflicts, but we're not going to go into that. And this doesn't always work also, but this makes life a little bit harder also, because now the programmer cannot reason about which address goes to which bank. Right? They can reason, but reasoning becomes harder, because you cannot purely randomize them, because the randomization function needs to be predictable, right? Because you're taking an address and mapping it to a bank. Okay. So let me finish this part. We didn't get a chance to go into GPUs, but we'll do that tomorrow. But basically, if you look at array versus vector processors, this is the purest distinction. Modern SIMD processors are a combination of both. They exploit data parallelism in both time and space. And GPUs are a prime example of this. Remember, array and vector. So let's look at the vector execution. This is a vector processor, right? One element every cycle. But this is really what it truly looks like today. The combination of a vector processor and an array processor. You do 4 elements per cycle, but you also do it in time. So which means that the first 4 elements in first cycle, the next 4 elements in the next cycle, the next 4 elements in the next cycle, until you finish all the elements in your vector by using 4 functional units in parallel. So this is really a combination of vector and array processor. And this is how things look like. Basically, you have this register file. You partition your vector registers. So vector element 0, element 4, element 8, ... go here. 1, 5, 9 go here. 2, 6, 10 go here. ... So this is called a lane. Basically, element 0s get added here. Elements 1s get added here. Element 2 get added here. So it's very basically, to enable this, you partition your register file so that you don't need a huge register file. Only part of your register file needs to be here. Another part needs to be here. Another part needs to be here. Just like we bank memory, right? Elements 0 are in this bank. Elements 1 are in this bank. Elements 2 are in this bank, ... right? So it's a beautiful structure. This is very simple. You don't need a huge register file. Collectively, you have a huge register file, but you can partition it into many small pieces. Okay, so let's have some fun over here. Basically, let's say we have an example machine that has 32 elements per vector register and 8 lanes. 8 lanes mean 8 of these, 8 functional units at a time. We can complete 24 operations per cycle while issuing 1 vector unit instruction per cycle. Let's take a look at the load unit, multiply unit, add unit. Each of them have 8 functional units, 8 lanes. You start with a load. You have 8 functional units, and you have 32 elements per vector register. So in 4 cycles, you finish the load. And you have 32 operations here, 8 operations per cycle. In the next cycle, you can start the multiply. 8 multiplies per cycle, 4 cycles, because you have 32 elements. In the next cycle, you can start the add. 8 adds per cycle and 4 cycles. That's the latency of the complete add. So basically, at any given point in time, you have 32 operations, 8 times 3, 24 operations. And here, once the load unit becomes free, you can start the next load. Once the multiply unit becomes free, you can start the next multiply. Once the add unit becomes free, you can start the next add, ... So that's how you keep a GPU or a SIMD unit busy. Okay. Let me finish this one also. How much time do we have? Okay, let's not finish this one. This is a good place to start the GPU lecture tomorrow. Hopefully you know what a vectorizable loop is. What is a vectorizable loop? Anybody who's brave and not sleeping? Or vectorizable code? Yes? Exactly, yeah. A loop where iterations are independent of each other. There is no loop. There's also a loop carry dependence. There is no loop carry dependencies, basically. And that's vectorizable. This is an example of that. There is no loop carry dependence here. And if we look at it, the iterations look like this. I'm going to ignore the branch over here. And this is a way of vectorizing it. Basically, you take these 2 iterations and you put them side by side. And you take more than 2 iterations in this case. It could be your vector length. You put them side by side, and for each instruction that is the same, you generate a SIMD instruction or vector instruction. So you have a vector load, vector add, vector store. That's how you vectorize the code. So if you have a good programmer, clearly the programmer can understand the iterations are independent and do this in their head. If you have a good compiler, the compiler could do it also, right? The compiler can say, oh, this iteration is independent of this iteration, and I can prove that all iterations are independent, and they're all doing the same thing. So I'm going to put them together and pack them into SIMD instructions, vector instructions. So basically, vectorization is a compile time reordering of operation sequencing. Basically, you can think of this as you're sequencing through this operation sequentially. Instead, the compiler figures out that this loop is vectorizable, so it basically reorders the sequencing such that iterations are happening in parallel, and each instruction in the iteration is a vector instruction now. Now you're basically, the vector instruction spans the iterations. So of course, to be able to do that, the compiler needs to make sure that these iterations are independent of each other. In this case, yeah, it may be easy. Although it may not be easy also, because C may be overlapping with A, right? So the compiler needs to make sure that these arrays do not overlap with each other, right? Such that they don't, a previous iteration does not override a later iteration, right? This is called loop dependence analysis. And if the compiler doesn't know the addresses, remember, the addresses may be generated dynamically during runtime. And if the compiler cannot figure out the addresses at compile time, it will not be able to vectorize this code. But as a programmer, you may have that information. You may say, oh, I'm never going to have an overlap between these arrays, even though you may dynamically generate, because you may understand some semantic information from your program. You can easily say, oh, there's never going to be an overlap. The compiler cannot prove it, so it cannot vectorize, but as a programmer, you may be able to vectorize it much better. So there are levels of knowledge that happens at the transformation hierarchy, right? You're the programmer at a higher level, and you have a lot more semantic information. Of course, if you're the programmer and you miscalculate and you're wrong, then you get a wrong program. And that's one of the problems with parallel machines. When you try to vectorize your code, you may get wrong program because you may think that these arrays will not overlap with each other. Right? So even this simple piece of program is not easy for the compiler, and it may not be easy for the programmer also to vectorize. Okay. So this is the summary of vector processing. We're going to move to GPUs. I mean, there's a lot to be said in this, and as you will see that also, there are other ways of executing this program, and we will see this in a little bit. But this is actually essentially the beginning of a parallel computer architecture course. How do you actually design parallel machines? How do you program them? And how do you make sure they work efficiently? And how do you make sure they work correctly? Right? And whose burden is that correctness, right? Because there are problems you can encounter at any place. If you think sequential programming is hard, parallel programming is much harder. Okay, so basically, this is a summary. Vector or SIMD machines are good at exploiting regular data-level parallelism, as we've seen, and hopefully it's clear from this picture. Basically, you perform the same operation on many data elements. This improves performance, this simplifies the design, and this improves energy efficiency also, because you fetch much fewer instructions. It's always the case that performance improvement that you get from any machine, any parallel machine, is limited by the vectorizability of code. So if you have no loops that are vectorizable, too bad. If 90% of your program is vectorizable, what's the maximum speed up you can get? Yes? 10 times, exactly. If 90% is vectorizable, assume that you have an infinite number of processing engines, infinite number of lanes in your SIMD machine, or infinite number of functional units. You can get rid of that 90% and you're left with the 10%. 100% divided by 10% is 10x. So you get 10x speed up in that case. So 10x is not that high, right, with infinite number of processing elements. So you really want your program to be very vectorizable in the end. So if only 50% of your program is vectorizable, whatever you do, you can get only 2x speed up. So you really want to increase the vectorizability of your code. If it's 99% vectorizable, you get 100x, which is still not that high compared to infinity. Okay, so this is Amdahl's law. You know this, basically, which means that scalar operations limit vector machine performance. And this is true for any parallel machine. If you have a multiprocessor, the non-vectorizable, non-parallelizable part of your code limits your performance, which means that as a parallel machine designer, you have to be smart. And Cray, when they designed Cray 1, where it's smart, they didn't say we're going to design the fastest parallel machine, but it was actually the fastest scalar machine of its time also. Remember the heterogeneous picture where they had the vector units and the scalar unit? They said we're limited by this Amdahl's law, so we're going to design the fastest scalar machine such that when we're executing through the sequential part of the program that we cannot vectorize, we're going to go really fast and minimize the impact of that scalar part. Does that make sense? So this is when people think about Cray, they think about it's the fastest parallel machine, but this is one of the main reasons, actually. They really optimize that scalar part. In fact, Amdahl's law, when it was written in 1960s, 1965, 67 to be precise, Amdahl, he did the analysis of the vectorizability of the programs at the time, like data-intensive programs at that time. This is 50 years ago, of course, very different programs. And he found that a lot of the programs are vectorizable by about 60% or so. So his paper was actually relatively pessimistic. He said that you need to actually invest into sequential execution to be able to make a parallel machine work, because only 60% of the programs, 60% of the program is parallelizable. So if you read Amdahl's paper, which I should have referenced here, but maybe we'll put it up online afterwards, you will get that. So never forget this. Whenever you design a machine, the part that you're not able to parallelize will come and bite you in the end. Okay, so SIMD has been very, very successful. Many existing ISAs actually include vector-like SIMD operations. And I'm going to show you examples of this. And you may have heard of some of these acronyms. ARM has, I don't know, maybe they have a new one right now. But Intel has AVX right now. They used to have MMX, which I will talk about. So what are these SIMD operations? These are actually a pretty limited form of SIMD. Remember this, we've already talked about the SIMD. These are extension instructions, basically. A single instruction acts on multiple pieces of data at once. And the reason they were introduced, as I will show you in the next slide, is because of graphics. And basically, instead of interpreting a data element as a 32-bit word, this should be 0 through 31, by the way, but that's okay. You interpret it as 4 8-bit bytes, right? And then you basically add those 8-bit bytes, yes?
What's the difference practically between an extension instruction and a regular?
Oh, basically it's a regular instruction, but it was added to the ISA later on. You always keep extending the ISA because you find out that, oh, you need this instruction to go faster. So x86 ISA, for example, has been present for a long time, but they introduced in 1996 actually, these MMX extensions. It's still a real instruction, but they're extending the ISA, basically. So that's a good question. I mean, for any instruction, the CPU can do something special, right? So initially, they were executed in a separate part of the functional unit. Actually, the floating point extension, for example, when x86 introduced it, there was a floating point coprocessor. So it was really executed on a separate coprocessor, if you will. Later, it got integrated into the pipeline. So I say extension here because it was extended, but I mean, you can always move existing instructions out of the processor also. But that's a very good catch. That's a good question. Okay, basically, instead of interpreting a value as 32-bit value and doing a scalar operation on two 32-bit values, we interpret a 32-bit value as 4 8-bit bytes and then do 4 adds, 4 byte adds, basically. And that's the specification of the instruction. And this is a packed add. It's called a packed add. You pack 4 adds where each add is 8 bits, 8 bits wide. Basically, that's a SIMD operation. Very limited SIMD, right? But it is SIMD. So let's take a look at Pentium's MMX operations. The idea is very similar. One instruction operates on multiple data elements simultaneously. It's very similar to array processing, actually. If you want to be a purist, this is really array processing, right? You have multiple data, and you're operating on them at the same cycle, at the same time. And again, this is designed with multimedia operations in mind, and we will see an example of it. So this is exactly the same previous picture with the numbers a little bit corrected over here. So what's the difference? There is no vector length register, because your vector length is really specified by the instruction opcode. So opcode determines the data type. Basically, an opcode can say, I'm going to interpret the 64-bit value as 8-bit bytes, and do 8, I don't know, adds, multiplies, whatever the opcode is. Or I'm going to interpret this as 4 16-bit words, and do 4 16-bit adds. Or I'm going to interpret this as 2 32-bit double words, and do 2 double word adds. Or I'm going to interpret as a single scalar 64-bit quad word in Intel's terms, and do that. And all of these are distinguished based on the opcode instruction that you have. Yes?
So if you have a 64-bit adder, for example, can you just turn off the carry?
Exactly, yeah. Basically, if you go back here, you need to enable this to make it work. You can eliminate the carries and do it that way. So you'll need to modify your adder to make it work, of course, and that's exactly what they did. This is the minimal thing that they can do to enable these operations without modifying the pipeline that much. Okay, basically you change your ALU control. Okay, and this is a beautiful paper. If you're interested in reading about this, this paper is actually one of the very clear industry papers that introduces this, multimedia extensions. And they introduced it because they figured out that there's a lot of this kind of operations, for example, on pixels, in graphics, multimedia processing, and Intel processors were not good at handling these operations because these were not 64-bit, not wide operations. These were usually 8-bit or 16-bit operations. And they wanted to do more operations per cycle. And that's exactly why it's introduced. So let's see an example. This is a simple example, which may look complicated. This is directly from the paper, and my copy was not that great. Maybe you'll have a better copy. But basically, the idea over here is an image operation. You have this picture of a lady, and you want to substitute the background, which happens to be blue, but you cannot see the blue over here. And lady is hopefully not wearing blue, and not have blue eyes, I assume. Basically, we want to substitute the background with this picture of the background image, which happens to be, I don't know, some tree, I guess. This is called chroma keying, basically, image overlay using a background color. So what you do over here, let's assume that the images are equal size. What you do over here is we would like to basically get a bit mask of only the blue parts or the non-blue parts. Of the image. So we operate 1, 2, 3, 4, 5, 6, 7, 8 pixels at a time. You load 8 pixels at a time into these multimedia registers, that they call them multimedia registers. And let's start with these 8 pixels over here. Basically, you compare those 8 pixels to this blue vector. So this is the encoding of the blue in terms of the pixel. And you check whether the 8 pixels that you've loaded from this image is equal to blue or not. Basically, that's a packed compare equal byte. That's what this stands for. You have each byte compared to, I don't know why it's a byte, but anyway, you can read the paper. But I'm going to assume it's a byte. Basically, it turns out that these 8 pixels that you have, this is not blue, this is not blue, this is blue, this is blue, this is not blue, this is not blue, this is blue, this is blue. And this pack comparison compares whether each pixel is blue or not. Basically, there's a value for blue. If it matches, you get all Fs, all ones. If it doesn't match, you get all zeros. So in this case, you can figure out which ones match and which ones don't match. So these pixels over here match, apparently, and these pixels over here don't match. So this must be somewhere from that part of the image. Make sense? Basically, you figured out which parts of the image are blue or not. You do it for the entire image, but this is one instruction. So you need to have a loop to loop through the entire image. And what you do after that is, if you want to do the overlay for the pixels that are blue, you want to replace them with the pixels that are corresponding in this image. For the pixels that are not blue, you want to replace them with the pixels that are corresponding in this image. That way, hopefully, you will get this image. Okay? And that's what this does, basically. This does a packed AND of this bit mask that we've computed based on which pixels are blue. And it replaces the blue elements with the data that comes from this blossom image. Okay, that was the word I was looking for. So the blue elements here get replaced with the blossom image. As you can see, we're ANDing here. And this is an AND NOT, or NAND, basically. We replace the 0 ones with the pixels that come from the lady's image. And then you do a packed OR on these results, such that you can combine the two images. And packed OR simply, these are 0 over here, we didn't modify, but we get the values from the lady's image. And here, the non-zero values come from the blossom image that we're overlaying into. And they would hopefully be 0 in the lady's image, or after this operation. And you basically merge them using a packed OR. Make sense? So it's pretty simple, actually. You just, and then you can encode this with all of these instructions. So you need to move. You need to move the data from memory into the MMX registers, and then do a pack compare equal byte, and then packed AND NOT, and then packed OR, and then you're done. And then you do a loop across the entire image, all of the pixels on both images. And this is an AND NOT, or NAND, basically. We replace the 0 ones with the pixels that come from the lady's image. And then you do a packed OR on these results, such that you can combine the two images. And packed OR simply, these are 0 over here, we didn't modify, but we get the values from the lady's image. And here, the non-zero values come from the blossom image that we're overlaying into. And they would hopefully be 0 in the lady's image, or after this operation. And you basically merge them using a packed OR. Make sense? So it's pretty simple, actually. You just, and then you can encode this with all of these instructions. So you need to move. You need to move the data from memory into the MMX registers, and then do a pack compare equal byte, and then packed AND NOT, and then packed OR, and then you're done. And then you do a loop across the entire image, all of the pixels on both images. Okay, so hopefully this shows you an example of where these SIMD operations, even in a very limited form, could be useful in image processing. And in image processing, you have millions of pixels, especially if you're doing high-resolution images, high-resolution videos. That's a lot of pixels. So even doing this on 8 operations is good, because it improves your instructions per cycle by 8, if you will, instead of doing it 1 by 1. But you could easily do it for 1 million pixels at a time, right? And that's where GPUs come in, basically. GPUs were initially developed to do the processing of things like this, images, videos, graphics in general. I'm going to give you a view of them in the more general purpose perspective. We're not going to touch the graphics parts a lot, because if you want to go into graphics, that's a course by itself, really. Both graphics hardware as well as the software. So GPUs, by the way, any questions on that image before? I recommend that you read that paper, actually. Maybe I should assign that as a reading rather than the other GPU paper. Maybe we'll have 2 readings, since these readings are really not covered in any textbook, but the field has moved a lot. If you don't know GPUs today, you're at a disadvantage very quickly. That's why it's not covered in the previous textbooks, right? Textbooks always follow what happens in real life. Okay, no questions, so we'll go to GPUs. So GPUs